Hello everyone, I'm Tony from Intel. Today I will present an empirical study on predicting uncorrectable memory errors from the correctable error history and show that there are no free predictors in the field. This is the joint work with Xiaoming Du. Here is the outline of my talk. First, we will briefly introduce the background of DRAM reliability and errors. Next, we will describe the task, the datasets, and the performance measure. After that, we will formally establish our prediction framework, present the cross-dataset empirical study of the individual fault-based predictors, and show that the predictors perform differently on different datasets. To accommodate the different characteristics in different datasets, we will then propose combining the predictors and adapting the ensemble to the datasets. We will show that with the cost of learning, the approach performs consistently. Finally, we will give the concluding remarks and the future work. A dual inline memory module composes of a few DRAM devices organized in ranks. Each device contains a number of banks, and each bank is a two-dimensional array of cells indexed by rows and columns. While we expect that the content read from the device should be the same as that written, in reality it may not. There are multiple underlying causes, to which we refer as faults. For example, soft faults like particle strikes. When DRAM wears out, non-reversible hardware faults get developed. Hard faults are found to be dominating in the field. In summary, DRAM is not reliable. To mitigate DRAM failures, error correction codes, abbreviated as ECCs, have been developed. ECC corrects the error bits in correctable errors, abbreviated as CEs. However, when error coincide, the error pattern may go beyond ECC's capability. The coincidence then becomes an uncorrectable error, abbreviated as UE. A UE typically leads to a system crash. As a problem at scale, it becomes one of the leading causes of failures in data centers. In some environments, the cost of a server crash can be significant. In those cases, one may consider replacing the DIMM proactively before UEs happen. This requires the use of predictive failure analysis. For example, if we see 1,000 CEs in the past 24 hours, the DIMM is predicted to experience future UEs and is to be replaced. The question then becomes, what is the right policy for proactive replacement? In our study, we addressed the problem of online UE prediction for proactive replacement. There are many DIMMs on an individual server. There is also a UE predictor with the accesses to the CE history of the DIMMs. When a new CE comes in, the error information such as the DIMM, the bank, the row, and the column is corrected. This triggers the predictor to perform UE prediction with the up-to-date CE history. If a predictive UE alert is generated, the cluster manager will get informed and migrate the workload immediately. A repair is then requested. One may choose to replace the DIMM either promptly or later in a batch. The data used in our study comes from different technology companies, collected from DDR4 DIMMs on the contemporary SkyLake and Cascade Lake servers with the same ECC. The micro-level CE address information is obtained from the Linux error detection and correction driver. We got 4 datasets from 3 top-tier technology companies with different scales and different time lengths. The characteristics are listed in the table. Note that some DIMMs with UEs are not with preceding CEs. Those DIMMs do not fit to our problem setting and are not considered in our evaluation. To measure the performance, we replay the error data for a predictor to run online UE prediction. If a UE occurs without a predictive alert generated from the predictor, it becomes a false negative. If the predictor generates a predictive alert at the time, we look for future UEs. If a future UE is found, it becomes a true positive. If there are no future UEs, it becomes a false positive. Precision gives the percentage of true alerts over all the alerts. A low precision implies a waste of good DIMMs in replacement. Recall gives the percentage of true alerts over all the UEs. A low recall implies that we suffer from more UEs. Since a high recall usually results in a low precision and vice versa, we use their harmonic average, F measure, as a balanced metric. We also formulate a cost model in proactive DIMM replacement with UE prediction. We define the unique cost of crash, repair, and workload migration. We compare the cost in the case of doing nothing versus that in UE prediction and migration. We hypothesize the 3 different scenarios with different cost ratios. We calculate the relative cost in all the scenarios, aggregate into their geometric mean, and then reach a single number of cost reduction. Here we formally establish our prediction framework based on 2 principles. First, the errors observed comes from the combined effect of both the hardware faulty status and the runtime context. For example, even if there is a stuck at bit of 1, we will not see an error if the bit is not accessed, or if the content stored in the bit is also 1. Second, if the error coincidence goes beyond the ECC's capability, it then becomes a UE. In our prediction framework, we first use the CE observations to infer the latent memory faulty status. We then correlate the inferred memory faulty status with the UE occurrences for predicting future UEs. Here we start from a cross-data comparative study on the individual fault-based predictors, which we will introduce next. The fault-based predictors used in our study are extended from our previous work. In that work, a column fault predictor is defined. If in a 24-hour time window, CEs are observed on no less than theta C locations over a span with the length no less than LC in a column, the column fault indicator is activated. We then predict that UEs will occur in the future. Here we depict a column fault example in a bank of 2-dimensional arrays. Theta C and LC are 2 parameters. A column fault is more likely caused by a circuit damage or an I/O drift in bit lines. Similarly, we define a row fault predictor. If in a 24-hour time window, CEs are observed on no less than theta R locations over a span with the length of no less than LR in a row, the row fault indicator is activated. We then predict that UEs will occur in the future. A row fault is more likely caused by a row address decoding failure, a word line damage, and so forth. We also define a bank fault predictor. If in a 24-hour time window, CEs are observed on no less than theta B locations over a rectangle region with the height no less than y and the width no less than x in a bank. The bank fault indicator is then activated. We predict that UEs will occur in the future. A bank fault is more likely caused by a bank circuit damage with a large area of impact. We further define an error storm predictor. If we see a large number of CEs in a short time interval, the indicator is activated, and we predict that future UEs will happen. An error storm fault is likely relevant to the DRAM circuit fault triggered in certain external conditions. We also take the most commonly used baseline, the CE rate predictor, as a reference. All those predictors depend on certain parameters. We take each parameter from a limited number of choices and tune the parameters for each dataset. We then obtain some predictor instances, which work at least best on one dataset. We report the performance of those predictor instances in the cross-dataset comparative study. Here we show the cost-independent F measure of the individual predictors. We also show the cost reduction of the predictors. Note that a negative cost reduction implies a worse cost given the UE prediction and mitigation. In the experimental results, we see that a column fault predictor performs better in 3 of the 4 datasets. Unfortunately, on dataset 2, column fault predictors do not perform well enough. However, on dataset 2, a row fault predictor performs better. Unfortunately, row fault predictors perform poorly on the other 3 datasets. Overall, different predictors perform differently on different datasets. There are no free predictors working universally well on all the datasets. We conjecture that it is due to the different characteristics of the hardware faulty status and the runtime context in those different environments. Now we try to address our conjecture, that is, to accommodate the different characteristics of the hardware faulty status and the runtime context in different environments. We propose to combine the fault-based predictors in a weighted ensemble. The weights are to be adapted to a specific dataset through ensemble learning. To make the ensemble predictor more powerful, we also incorporate less well-performing indicators studied in our previous work, with the hope that they can contribute to such a combination. We have our fault indicators and other micro-level indicators defined. We have the memory error data. Note that the datasets are imbalanced. There are much more samples without UEs than samples with UEs. We then apply the ADA U-boost algorithm. This is a variant of the state-of-the-art ADA boost algorithm, adapted to imbalanced datasets. Given the error data and the defined indicators, we generate the weighted training data. In the initial weights, we emphasize the samples with UEs. A simple rule is learned from the weighted data. This rule simply takes one indicator as the input and determines whether UEs will happen or not in the future. The data is then reweighted, emphasizing both the incorrectly classified samples and the samples with UEs. We repeat the process of rule learning. The final predictor is an ensemble of the rules learned. In machine learning experiments, we need to partition the data exclusively into training set and test set. Here we use the standard tenfold cross-validation in evaluation to make the results comparable with those from the individual predictors. We report both the F measure and the cost reduction. We see that the ensemble predictor learned perform consistently on all the datasets, reaching both the optimal F measure and the cost reduction in all the cases. This indicates that the ensemble predictors are able to capture the dataset-specific characteristics. We have some further analysis showing that in ensembles learned from different datasets, the top individual predictors with large weights are different. We compare the RU boost algorithm with support vector machines, random forests, and the basic RU boost algorithm. RU boost performs most stably than the other methods. We also show that the ensemble predictor learned from one dataset does not work stably on the other datasets. More details can be found in our paper. The good performance measure is not free, but comes with the cost of the data from the corresponding environment for learning. To conclude, we have performed a cross-dataset comparative study on uncorrectable memory error prediction. We show that those fault-based indicators perform differently on different datasets. We conjecture that this is due to the different characteristics of the hardware faulty status and the runtime context in different environments. There are no free predictors in the field. We propose to learn ensemble predictors from the datasets. The learning approach performs stably by capturing the specific characteristics in the data. Today in our datasets, we do not have the error bit information or the DIMM manufacturer information. We plan to collect those information in the future. With those information, we expect to get a better understanding on the different hardware faulty status, and probably a better prediction approach can be built. Here is the end of my talk. Any questions or comments are welcome. Thank you.